started. Welcome back. Congratulations on making it to a Wednesday. That's a big accomplishment in this course. On a week to week basis, we should pride ourselves on making it through the week. Um, we'll start off by just continuing right where we left off on Monday. We were talking about some of the syllabus related items and going through the schedule. And then I'm going to try to connect that back to some of the relatively straightforward big picture topics we were talking about at the end of Monday. So where we had left off was, um, talking about our communication mechanisms for the class, and I had mentioned the class Discord. We're up to, I think, about 125 students who've signed up for that. There's 154 signed up for the class. Uh, Ideally, we should get to 100%. We don't get 100% coming to class. I understand that. I'll try to incentivize that somehow. I'll somehow get cookies or something for the whole class if we can get to 100% Discord sign up. I think it's already provided some value in just asking questions and getting pretty quick answers. Um, I'm guessing though, preaching to the choir here, that if you're here connected to Zoom, you've probably already followed that instruction and are on the Discord already. But for your friends who haven't done so yet, it's just a couple clicks away, and convince them to consider doing so. Here's another view of our weekly schedule. Um, we are on Wednesdays now, and we have our Zoom lectures already sort of figured out, and it's going to stay that same link on a week to week basis here. Um, Also, you can see the various lab sections, and that is starting today. So for some of you, you'll be going immediately to Discord after this class gets out. I guess there's a little bit of that 15-minute break in between these scheduled things this semester. And for the remainder of you, it's later today as well as on Thursday. So that is the plan. That these are synchronous labs, and you will be clicking on the appropriate link inside Discord. Just getting a chance to meet your TA, meet your classmates in your individual section as well. And it may not seem that necessary in this first week. Those of you who've already taken a look at it say, "Well, I've got this." I do guarantee you, it's going to become more and more necessary as the semester goes on. We also have our layout of the currently scheduled office hours here. I've already had a few students in office hours, and that's wonderful to see. And as the semester goes on, if we need to add more hours, we can certainly do so. That's just my version of how we generally all feel. I think on a Monday, happy, life is full of potential, ready to go about the week and dominate. And then over time, still pretty happy on Tuesdays. We're getting close to that Thursday where life, I think, starts to throw a lot of things at us, and we know how Fridays can go. With by the end of it and the amount of work that you have to do, that can be a pretty stressful environment by the end. So that's my thought on how our week generally proceeds. So um, that's our general layout. Those of you who are here on Wednesday, we see that label of quiz, and we'll get started on the quiz very briefly here. Give a few more minutes for folks to sign up and show up for that. And then I call it Friday fun. I think every day of the week should be fun for this class. Something that's a little bit off the scheduled textbook for Friday is what I'm going to try to do on a week to week basis in this class. Talked a little bit about the course tools already, and there's two major ones. You can think of the remote servers that you're required to access this semester as a third course tool, but that'll be common across a lot of your courses this semester. That's that VLab, or the virtual desktop instances. It seems to work pretty well. As any remote setup, it's more reliant on your internet speed versus your computing speed, but it gives you a nice kind of contained environment where you should have some guarantees that the stuff you need to get working will be working there. And the primary tool you'll be spending your time in this semester is that Model Sim tool. We'll keep coming back to Model Sim as the semester goes on. You're also simultaneously or concurrently learning how to become more expert in that tool, as you're also learning more about VHDL design and computer architecture in this course. Oftentimes, that's the real challenge in designing something: is how do I get the tools to do what I need them to do, more so than what is the exact perfect line of code that I need to write. We're very rarely stuck on lines of code. It's much more commonly that, how do I see the result that I need to see? How do I configure this tool to do what I need it to do? The second tool that you'll be using a decent amount this semester is Mars. Mars is a MIPS simulator. There's a direct download link from the professor at Missouri State University who develops it or originally developed it. It's also on Canvas under the resources tab. You don't need to download that yet. It's just a little Java jar, and you can just run it on your own local machine, or you can run it on the VDI instances. It's meant to be something of an integrated development environment for MIPS. For our purposes, we're using it generally just as a MIPS assembler and a simulator for a simple machine model for a MIPS 32-bit implementation. It's actually a pretty nice tool with some depth to it. It's got some features that aren't very well documented that can be very helpful for debugging your Mars code. Um, that will you will find that helpful in terms of both learning how to become a better MIPS assembly programmer throughout the semester, as well as in debugging your own processor. And later on in the semester, what we have is an integrated testing framework for the processors that you're building that basically are running Model Sim and Mars concurrently and comparing the results with each other on a cycle by cycle basis, or at least on an instruction by instruction basis. And that's kind of fun. That'll give you results such as, you've written this assembly code and you're testing it on your processor, and it works for 47 instructions, and on the 48th instruction the value of this register is different between Mars and between your implementation. And from this course's perspective, we trust Mars as being the correct result. So that tells you exactly where your bug is. You can then look back and see, okay, that instruction, that cycle has this bug in it somewhere. Let's look just at that versus looking at the whole processor as a whole and not knowing really where to start. That'll come a little bit later in the semester. I did talk about this in a separate video I uploaded, and it's on Canvas, but I think it's important just to talk about the various grading policies just pretty briefly here. Those are the primary components of the grade. So today is our first quiz. It's a low stakes assessment, as you can see, based on the overall score. You'll also see, based on the nature of the quiz, it is a very low stakes assessment here. The two major pieces are going to be the lab slash project. Um, they're basically worth 50 points on a week to week basis this semester. And so the project's worth more than the labs, but they're ultimately worth the same based on weekly effort for them. And then there's 3 exams in this class, middle of the semester, 2/3 of the way semester, and then the final exam for this class. I haven't quite figured out exactly how I want to proctor the exams this semester. There's a lot of different ways I'm allowed to do it. We can do it. The dates are set, but how it's actually being proctored is not yet decided. Um, my goal is to optimize my grading time. So whatever mechanism I can come up with that minimizes how many hours and hours and hours I have to spend on grading exams. I'm looking for those type of solutions. This is not tongue in cheek. We can absolutely shoot for a class 4.0 in this class. I never, I believe, ask any question that's attempting to trick the class. I never ask for anything to be done in the lab that I know can't be done, that I know the general pitfalls along the way. You do have to put effort into this class. It is a decent commitment on a week to week basis. Um, the complexity of the designs you're working with, it does ramp up, but it is a very doable class, and there's quite a few students who put in the hours and get a very good grade in this class. And I'm happy if that's the end result, that all of you decide to do that and you all get A's. I'm perfectly happy with that. I'm also a very big fan of collaborative study and discussion and helping each other learn throughout this class. I do differentiate between a collaborative environment for learning and studying together and helping each other with understanding questions in the class. I love that. But your actual individual submissions, that's the individual homeworks, that's certainly the exams, that's supposed to be representing your own work. So uh, that's true of a lot of classes I think you're taking. I don't think that's unique to this class, that we want, on one hand, you to be collaborative and learn with your peers, and that's great and all. But then when you submit something and you put your name on it, that's an academic honesty issue, that that's representing your work and not someone else's work with just your name on it. The labs, we're going to be starting off this week, and they're going to be individual labs. I think it's 5 weeks into the semester, we're going to start to team up, teams of 2 to 3 of people inside your own lab section. And that doesn't necessarily make life any easier. We know that when you're working in lab teams, um, there's work that can be shared, but then there's all the complexity that goes with working in a team and all the potential headaches that happen. Um, so managing that is one of the learning outcomes for this class, and it's an ABET outcome for our discipline as a whole, of the ability to work in diverse teams and to work in a collaborative environment. And I think even in our remote environment where you may not get to meet someone face to face the entire semester that you're working with, it's a pretty good skill to continue to develop. And we'll be developing that as part of the lab projects for this class. My other two, just very high level grading policies, is just given the size of the class, just given the number of assignments, given the relatively lean budget for teaching assistants that we have as a department, just generally we're not doing late submissions. So you don't have to ask, how many points will I lose if I don't submit this thing on time? The answer is generally, all of them. So submit things on time. Obviously, if there's a major life circumstance that happens and that causes you to, miss something, and we can always talk about that, but please do let me know. But it's not a, can I get an extra few hours here? That's not, we're not doing that. I don't want to have to be able to keep track of that. Um, and we're not planning on doing that this semester. So keep on top of your schedule this semester. Keep things submitted on time, and it'll be a pretty good pipeline as we go. In terms of regrades, and certainly that's always a valid thing to request. I'd like to keep it within a reasonable window when your grade is returned. So you submitted a homework, you got a grade back. Please do take a look at that in Canvas. The TAs are supposed to provide some written feedback when they take points off, and if they miss something, which certainly happens, we all make mistakes, put in that formal regrade request. That can be an email to the TAs, that can be through Discord, but within 1 week after the grade for a given assignment has been returned. Those are my policies for you. The final syllabus item is really just my goals or my hopes for myself. I really do love this material, and I know that this may not be your lifelong goal to become a computer architect, but my hope is to make this experience pretty enjoyable and informative. I do think now that you're at that 300 level of the computer engineering curriculum, you should be learning a lot in your courses. You should feel that you got your money's worth this semester, even in this virtual environment. I feel like that should be my goal. That okay, I took this course and it was expensive for not meeting the instructor face to face all semester, but I learned a lot. That would be a great outcome of this course. My goal is always to try to make the assignments fair but challenging. That's labs. That's also exams as well, and also certainly to motivate you to learn more. For some of you who are taking this effectively as an elective, depending on your major choice, this could be a terminal course in computer engineering for you, and that's fine. But certainly for the computer engineers or those who are in software engineering, electrical engineering, or cybersecurity who want to go more down this path, there are a number of really fun classes to take. And I list a few of them there. Uh, the one that I will be teaching in spring is CPRE 480. So as we learn more about computer architecture, there's a whole separate class on looking at graphics architecture. How do we build graphics processing units? And we do go through and we build one by the end of the semester, and that's a very fun class. And that would be for people who take this class and say, I want more of that. I want to crank it up a bit more, and I want to see what else I can design. 488 is the Advanced Embedded Systems class. 482 is offered in the fall, and that's the Machine Learning Architectures class. Any of those would be really great follow-on classes if you're enjoying this. And I feel like it's my goal to motivate you to learn more on this topic, even though it may not be necessary for you. If you look at my general teaching ratings, not the official ones, if you look at Rate My Professor for this course, you'll see that mixture of, this is a challenging class, but at least the resources are there for you to succeed, and that's pretty important to me. I want to continue to do that throughout the semester. So let's take a brief break right here from the lecture one content, and I want to bring up our class schedule, and everyone can see that. Okay, I just wanted to double check that that's the case. This is our class schedule, and let's take a minute, and I'd like everyone actually on their own devices to then navigate to that same page as well. So log into Canvas on your, for this one you can use your phone, but in general, I would want you all to have your laptops handy as you're navigating the Canvas and interacting with the course. And you should then, when you log into Canvas for this course and you click on it, you get to that general info page. You'll be navigating then to schedule, and then everyone can now click on quiz number 1. And in Zoom here, I will type in the chat for the actual code. It's listed there, but it may be hard for some of you to read. And it should be accessible. So what I would appreciate, I never know if these things work until the minute we start. Let me know now if something seems broken, but otherwise, if not, please get started. I'm only going to give us, a couple minutes to get our. Thanks, David. I'm only going to give us a couple minutes just to make sure the technology works. The actual quiz shouldn't take you more than a minute or two. So just take a couple minutes and get started on that. And I can moderate the quiz on my end. It is open until the end of the class day today, but this is not a quiz that should take you. There's not hours of typing. It should be a pretty quick quiz for you to be able to take. And I should add that if you went through it and you clicked something wrong, uh, my goal is for you to get 100% on this quiz. So go back and take it again and correct what part was wrong. Um, that's fine. It's also not the end of the world if you get a 1.5 out of 2 on this quiz, but you should be able to get a 2 out of 2. So I hear from a couple of you who are, and let's take the time and do this right, who are not able to get it to work. I do wonder to what extent it's not doing all that much from like a web browser perspective. So I'm here in the student view for the quiz. Click take this quiz, submit, and then I don't want to I don't want to add that. Um, and then the question should show up there. My other suggestion would be to try a different web browser or a different device. I'm using Google Chrome here. Um, you do probably do need to make sure that your login stays valid, for this to be able to work. But that is what I am doing, and it seems to work. So the password is case sensitive. Um, so hopefully people are figuring it out. Oh well, click out of that. By and large, we are getting there. We do have until the remainder of our class time today to figure this out. Getting lots of questions here. Just trying to keep on top of them. It's a little hard to moderate those questions as we are going. Someone asked about, is this a good class to be taking notes on paper? I actually struggle with that a little bit myself. I am very much a paper note taking person, trying to switch to sort of all digital note taking. If you look at the video I uploaded yesterday, my handwriting is very difficult to read in the digital format, and it's trailing off to the right. I do recommend taking notes, and it doesn't mean you're writing down everything I say. You have the video; you don't need to do that. The closed captioning works pretty well on YouTube. You can actually just see what I've said as opposed to having to write it down. Keeping track of the big picture items of things that are either tips and tricks or just the big rocks of this course, the things that seem important to remember. That is a good approach to take. You won't then wind up with pages upon pages of notes, um, but you'll have a very small little binder of notes that I think that'll be helpful to review. Definitely, when it comes time to plan for an exam, I do like students to take sort of a one page of notes of what they think was most important to be on an exam or what could be on an exam based on our review session that we have together. That really does force you to focus your thoughts here. Okay, it sounds like based on the feedback so far that we are done with the quiz by and large. Reach out to me if you're still having problems. We can just do some tech support. This is low stakes, and I want it to continue to be low stakes here. Someone did ask about CPRE 480 in the spring. That is the plan that I am offering it this spring. It hasn't been offered in about 6 years. That's a whole separate discussion. I've put several hundred hours this summer into building my own GPU. From on my FPGA board that I have sitting here in my little home office. It's not quite ready. I'll show it at some point this semester when it is ready, so you get a feel for the kind of stuff you'll be working on in 480. But both 480 and 488 would be great classes to take in the spring. Probably don't take both. If you're a junior, you could take one this spring and the other one the following spring as a computer engineer, and that would work pretty well. Okay, so congratulations on the first quiz. Many of you now have a 100% in the course. And that was my goal, as I said. Let's keep it up. Okay, so back to our main topic at hand, talking about the levels of representation in this class, and that translation from high level language, where high is a relative term here, whether you consider C a high level language or not. It compared to assembly, it is. From our translation from our high level language program in C in this example here, where the compiler's role is to take that high level language and to generate the assembly representation for a given ISA in this case and for this class in MIPS. And it will not take very long in the class where you look at this example here and you can pretty quickly see that assembly language equivalent to what MIPS would look like. Assembly language is still a human readable format. That is still our format for understanding how to interface directly with the machine. But the actual machine itself is really just understanding the ones and zeros, right? The so called machine code or binary code or object code where the ones and zeros correspond to the representation, the encoding of those individual instructions here. There's definitely benefits of operating in higher level languages, right? Higher level languages are closer to natural language, so it allows us to use our human reasonings to be able to more efficiently, more productively interface with the computer to implement some application. That in its own right is its own academic research development area of programming language design, right? What type of programming language features are most appropriate for maintainability, programmability, productivity, debugability. In this class, we don't worry about that. We just use C, and so we've chosen our high level language there. But that's definitely the advantage of higher level languages. Later on the semester, we'll talk a little bit about how compilers really exist to enable that for us. They help us deal with that abstraction of a higher level language by being very intelligent with how they produce efficient, optimized code for a given target machine. Because of those advantages, very little programming is done, at the assembler level. What is kind of interesting about that statement is 10 years ago that was absolutely the case. And 10 years ago that was a criticism of a course like this, or if you took a microcontrollers course that was effectively an assembly programming language course, that well, no one programs in assembly anymore. Why are we learning this? We could still make the argument that it's important to learn. You got to try it once, and then you'll really understand the rest of the machine that much better. That is all still true. But these things are cyclical, I guess. Assembly language programming is much more relevant today than it was 10 years ago. And I'm not just talking about microcontrollers and trying to squeeze the last bit of performance. Computer architecture evolution, and we showed that graph on Monday of kind of performance leveling off, and the computer architects need to get busy again and need to start developing new abstractions and new optimizations. It's also the case for the programming model. More and more performance critical programs are dropping into assembly. You see it on a day-to-day basis. to be able to take advantage of what modern processors are able to offer. So it is kind of a funny thing that there was definitely a period of time where the assumption was the compiler is better than you are, than we are collectively here. The compiler does a better job than you can of generating code. Don't even try. That is becoming less and less the case, and not more and more the case. You can still get by with never looking at assembly as a programmer. Certainly, people do it every day. But as those who are trying to really meet some criteria for their system performance, power, real time constraints, more and more designs are having to drop into assembly for those critical reasons for increasingly esoteric assembly code as well. And that's kind of a fun thing. So what's old is new again in the computer architecture community, in the programming community as well. I think both are equally true. Um, we talked a little bit about what that microarchitectural machine organization means. I didn't define it that clearly on Monday, but it's the principal functional units of your system and how they're all going to be interconnected together to implement a given instruction set architecture. And that ISA tends to have that description that is this register transfer level. We will see some examples of it. The textbook, the so-called green sheet for MIPS, that's that first page of the textbook, or I have it uploaded as a separate PDF on Canvas, that uses that RTL format to sort of formally define the semantics of the assembly level. We have an add instruction. It takes the two registers encoded by these register fields, adds them together, and stores the result back into this third register encoded by this register field. We'll be spending a lot of time on microarchitecture this semester. What are the core components that we need? Some of those terms hopefully don't sound completely foreign to you. And how do we interconnect them together? And then in the lab, so in class, we do it kind of at a conceptual level, at the PowerPoint level. In lab, we are doing how do we actually implement that? And it's not a lot of lines of code, but it's a lot of design for those lines of code. This is kind of an interesting time to be looking at MIPS as an ISA as well. This kind of data that I was trying to represent here is actually very hard to find in public sources. This is sort of a closely held investor secret with the relative popularity of different ISAs is not something you can quickly Google. You have to pay a lot of money for that information. I can tell you the market cap of all these companies and how much they're each worth in terms of billions of dollars, but in terms of how many chips are sold for a given ISA is actually very hard information, of recent information to find. But this is just one that I was able to find looking at two different classes of ISA. You've heard me throw out the term x86 already, and I realize, depending on your generation, that's not a term you use that frequently. x86 refers to the original, Intel processors, the 8086, the 286, 386. That has now just become kind of a shorthand for Intel ISA, even though they don't use that term themselves at all anymore. But we still tend to use that term referring to Intel and Intel compatible core ISAs. So that's your AMD processors, that's your Intel processors. They still support, code you wrote for an 8086 processor released in 1978 will still work today, but it's quite a bit on top of that as well. But that's that first chart here. That's the blue part of that chart where it's pretty clearly dominant in terms of processor market share. This must be a relative chart because obviously they don't add up to 100%. But what we've seen over recent years is this emergence of ARM as an ISA that's equally as old as Intel 8086 or x86, but has become just more and more popular over time, and increasingly so. That the likelihood is that you personally own many more devices that have an ARM processor in it and use the ARM ISA than actually have an Intel chip in it and use one of the Intel variants of ISAs. We could talk about that for a couple of hours. There are there are very few computer architecture reasons that's the case. I guess I'll say there's technological reasons that's the case. There's very few CPRE 381 reasons that is the case. There isn't really anything that interesting about ARM compared to MIPS, for example. They're extremely similar. If you accidentally bought the ARM version of the textbook, I want you to get the right one or download the right one, but it's close enough. You'll be fine. It's so similar, and they were developed at roughly the same time. There's a lot of economic, there's a lot of business reasons why that is the case. There's a lot of company management reasons that may be the case as well. But we are seeing, definitely a sea change in which really it's a function of just the number of devices and the type of devices that consumers buy. And that's my attempt to kind of show that we just don't buy desktop PCs at nearly the same level as we used to in terms of the overall market share. Whereas we do buy smartphones, smart devices, tablets, things of that nature, and those are almost 100% market share. Running on ARM ISA or some variant of the ARM ISA, and so we are studying MIPS in this class. It is very similar to the ARM ISA. We are studying an ISA that's extremely industry relevant for that reason. Um, I think one big takeaway from this course, though, is that we're going through this one example of an ISA in some depth, and the video I uploaded yesterday talks about let's build our own ISA and let's see what happens. And you can take a look at that offline. Um, they're all have much more in common than they have differences. So we could have built a computer architecture course that uses Intel assembly. Uh, the core principles would still be exactly the same. We could, and we sometimes debate building an ARM version of this course where we just switch to that version of the textbook. I'd have to change a few lines of code, in the lab. It's not a fundamental change what we were doing. Um, but we learned the core principles through this one example, but it's an example that's increasingly relevant in terms of penetration into industry of usage in consumer devices. It's a highly relevant design to be looking at. We're doing okay. I'm missing this feedback mechanism, at least in that if we were in a classroom, I could count how many people are asleep and work from there. But I can see the video stream. Let's see. Anyone sleeping on camera? At least if you are, you had the good sense to turn off your camera for sleeping. Well, thank you for that. Um, Fine. I don't really know what else to do but to keep going. There's a lot of stuff I want to get to really cover the rest of this. This slide, although we've already seen, the five main components of the computer. Yes, there's no banana listed here, or there's nothing called an engine in a car. That's our vehicle. Excuse me, no, nothing called an engine in our computer. That's our car analogy here. Um, the other big picture concept for today, which we are switching gears a little bit here, looking at what's happening underneath our high level representation of our program, right? From our C code that we write to specify our application to what our compiler generates for assembly to that underlying machine code, the ones and zeros here, and how that maps to our traditional layout of a computer, and that's our big picture. That's referred to as the von Neumann architecture, von Neumann computer. The other term that the textbook uses quite a bit, which is a valid term, is the so-called stored program computer. And I never know when I introduce this topic, and the textbook does it in chapter one as well, whether at this point in your computer engineering curriculum in the courses that you've taken, is this blindingly obvious or is this an important topic that we have to cover, in a lot of detail? So I don't really know because it's one of those things that once you learn, you never forget. But when did you learn it? Did a course cover it? The idea behind the stored program computer, uh, if you think back into von Neumann's day, and that's certainly a mathematician and we'll call him a computer scientist who's a very interesting life story. And you can look up John von Neumann and see what things he had accomplished in his life. When computers existed back then, you could so-called program a computer, but it was knobs and switches or some hard coded memory configuration that was the program for that computer. So his philosophical concept, and he's not the only one who came up with this idea, but it gets his name attached to it, is that we can think of our program, our instructions, our assembly instructions for the loads and the stores and the ads and things like that, as just being data. Again, I don't know if this is blindingly obvious or earth shattering for you. That data is data, okay, and needs to be stored in memory. But instructions can also be thought of as data. That we have this code, the machine code for the implementation of our ISA, and we can treat it as just another blob of data in our system. And that's what I mean when I say here that instructions are stored in a linear memory array. That's just a fancy way of saying instructions are just data. Instructions are stored as a memory array, as just ones and zeros put into the memory here. And it also implies that you have a compute model in which we load an instruction and then we process that instruction. Then we load the next instruction and we process the next instruction. It doesn't require that there's no parallelism in the system and that everything is purely sequential. But that was the implication, at least, originally as designed. So as opposed to knobs and switches being the way we interface with the computer, or some you can think of it as flash or something, but some firmware in the system, we have instructions as data, and so instructions can themselves emit other instructions. Now you can have compilers and operating systems and things like that. It's all ones and zeros at the end of the day. Code isn't this wholly separate thing from data. It is given special treatment than just data as data, but ultimately in our system, it is just ones and zeros. And I think if you've got that, um, we maybe have to remind ourselves of that occasionally as we're elbows deep in debugging our MIPS implementation and we're just not sure why this instruction is doing what it's supposed to be doing. But remember that, yeah, the instruction is just a 32-bit value for MIPS and it's just data. And why aren't we loading the data that we want to load for this instruction? And you work logically backwards from that concept. And it does tend to simplify what you're ultimately debugging. It's not some mystical thing. Again, the computer's only understanding those ones and zeros. Your job as the designer for the microarchitectural implementation is how do we see how the computer gets the ones and zeros it's expecting from that translation from the high level program where we have, again, some assembly instructions that are getting emitted to then corresponding ones and zeros in our machine code implementation. And one thing that MIPS does better than, I'll call it, just competing ISAs. A little bit more cleaner than ARM, but they're very similar there as well. Is something we will go into in quite a bit more detail, but is also illustrated on this slide here, where we have an assembly language program, and we don't need to know all the semantics of this instruction yet. But I'll just tell you, take the value in register 4, add it to the value in register 2, and store the result back in register 2. That's the add instruction. And MIPS was designed with an extremely clean breakdown of instruction encoding from assembly down to machine object code. It's possible as designed, they just didn't want to put as much effort into building a complicated assembler. But in practice, that leads to very simple logic for figuring out which instruction is which. And we can see, and we don't need to know why that's the case right now, but we can kind of see, or at least in a hand wavy way, we can kind of see, and there's some swapping going on here, which is sort of frustrating, but that's just how it's done. How that encoding is happening. We don't need to know the details yet, but we can see, yeah, there's register number 2, and we can see the binary encoding 2 for 2 here, as well as for here. We have a binary encoding for 4, and that's corresponding to 4 right here for our assembly instruction. And this is definitely more hand wavy now, but based on the 2 arrows that I've drawn here, we have something referred to as an add instruction, and that add instruction is encoded via some bits stored here, as well as some bits stored here. And that is something that MIPS does relatively well. This stored program model allows us to then say, we want to have an add instruction in our system. We want to execute an add instruction. We need to just make sure that we've stored those 32 bits of data into our memory at the right location, and then we have to build hardware that knows where to look for those 32 bits of data. And then after that add instruction is done, we then need to look for the subsequent instructions. And not belaboring the point too much, you can see some of the distinctions between your add instruction and, in this case, your store word instruction. It's a different instruction, so the encoding of it's going to be different. The processor is going to look at this field and it's going to say, in your implementation, okay, new 32-bit value came in. Is it an add instruction or is it a store word instruction? I better look at these 6 bits and determine if that's the case. I've determined it's an add instruction. What value should I be loading to add? Well, I should look at these bits and figure out if that's the case. That's what that stored program model allows us, and all architecture allows for that. At a higher level, you can think of it as interfacing with the 5 main components of a computer. We have that starting point. Before our user application is wanting to run, we have to grab that machine code to bring, or grab that object code and bring it from the outside world into the memory, into the computer itself. You can think of that device as being just a hard drive or something. You know, you don't have to worry about it being someone typing in the ones and zeros manually or things like that. But from an input device, just think of that as off storage, off chip storage that you have there, um, and bringing that in to begin with. Now, there's a little bit of a chicken and egg there, right? And we won't belabor the point too much because we do very little of that in this course. That well, there needs to be some code to tell the system to do that. Chicken and egg problem? Who is telling the processor to load that? Well, that's the role of your firmware, your boot system, your operating system, your VM, whatever is underneath your user application. But someone is telling the system, okay, start off and grab those ones and zeros there. And someone had already asked, and it's a valid question. What are these gaps for? Those are meaningless gaps. Those are allowing me to separate out the opcode from the other fields. In memory, there's no gap. It's just a big string of ones and zeros there. You'll find that helpful though when you're trying to figure out, what is what in a given instruction. It's just a 32-bit value. So we grab the values, and then those instructions are just stored in memory. And again, that's the von Neumann stored program concept. Data is data, and instructions are also data. And memory holds both, and it really can't tell the difference. The memory certainly can't tell the difference. The operating system tends to have some way of keeping track of that. We can talk about all the security implications of merging instructions and data, and that's a whole separate course that we should probably be teaching in this department. But conceptually, at least, data and instructions are all just these binary blobs that are in memory here, just 32-bit strings of zeros and ones for our 32-bit architecture. So the object code is stored in memory until the processor is ready to then fetch them. And this is the so-called instruction fetch stage of a processor's implementation. We will have to build logic, and it's part of the control logic that is figuring out what instruction is next. You don't need to know why yet, but it may sound a little familiar when we get to that. What instruction is next, what address in memory that corresponds to, and to actually do a read from memory. So we can talk about load instructions that actually read data from memory, but every instruction is actually also a load instruction, right? It's reading a value from memory corresponding to what that instruction is going to be. I'm seeing lots of good questions, but none that I feel obligated to answer because we'll get to all that. Good questions, though. I'm glad you guys are thinking about this and engaging right now. So the processor requests those values, and then somewhere inside the control logic is the actual instruction. So it's in some internal register at that point, or it's at least in some wires inside the CPU at that point. It's been loaded from memory, and then the next stage after instruction fetch is instruction decode. I have grabbed a 32-bit string from memory. I need to figure out what it is. And that's the control logic's task as well. And it's looking at those fields that we talked about, the ones, and that may be a little hard for you to see, the ones that are shaded kind of blue here are the bits that that we will be building hardware to look at for a 32-bit MIPS implementation that say, yes, in fact, this is not just an add instruction. It is an add instruction that takes the contents, and the color coding is a little hard to see. So you should look at the slides offline to see the color coding that I had in place here. These kind of darkish blue indicate that it's an add instruction that is taking the contents of register 2 plus the contents of register 4 and storing the result back into register 2. And so we'll have decode logic as part of it. And the decode logic is then going to send these signals to the data path element. That's the actual adder. That's the actual register file. That's the hundreds of muxes you'll eventually have in your design there, controlling those muxes. That logic is generating all those signals that then connect to those components, those functional units in your microarchitectural implementation. And that's the so-called execution stage. We've decoded the instruction. We know this information about the instruction and now what that implies. And it ultimately becomes kind of a big spreadsheet, and we'll design that spreadsheet as the semester goes on. And now we have our data path elements that actually do the addition. There's an actual adder there generally, and that's doing the addition. There's an actual register file somewhere in here. We'll talk about that, but that's there to store those intermediate results corresponding to the 32 different MIPS 32-bit registers. And that's the execution stage. Execution can be a lot more complicated than just an add, but conceptually it's the same concept. We fetch from memory, we decode and determine, yes, this was an add. We then execute that add instruction, and then there's the next state where we have to figure out now, what is next. So there is some sort of, you can think of it as a state machine. We don't implement it as a conventional, at least in this class, Moore or Mealy machine, but it is effectively a state machine that says we've fetched an instruction, we've decoded the instruction, we've executed the instruction. Now we go back to fetch, and now we figure out what's next. And with that von Neumann model, the logic for figuring out what's next is relatively straightforward. You'll spend a lot of time debugging it, but it's relatively straightforward conceptually, which is we had fetched this add instruction, and it's an add instruction. We should go to the next instruction. So if we had some pointer into memory that told us what address was originally corresponding to that instruction, we would need to do effectively a +1 to that address and say, well, we fetched the previous instruction, now we need to fetch the next instruction. And so when we talk about computer organization in this class, those are the primary elements that we are having to design and implement, right? All the control circuitry to do the fetch and to do the decode and to issue those signals to the rest of the data path's functional units to tell it, hey, do your job. We have an add instruction now. Let's do our job and let's do the add instruction. And then the data path, you also need to design those elements. We could spend a whole semester on designing really efficient adders and multipliers. There's a lot of things that people have looked at over the years. But we'll start with relatively straightforward ones. But the data path needs to have that circuitry to do that execution. So those are the function units. We will build a register file, we will build the MUX and throw 100 of them onto the design for us, and some way of interconnecting all those things together, as well as loading and storing values from memory. And I think, the remainder of that completion is we have our actual execution. Ultimately, we've added and subtracted and multiplied and stored some things back into memory. And now we need to put it somewhere. The application is done, or we need to make sure that we've stored a result back out. That's now using that output device, where again, if you just want to think of that as your hard drive, as your storage, that's fine. We need to have that mechanism in which the data that has been generated can then be output and reside back into memory. And then that's where it goes. And that's our major execution stage. We don't do very much with devices in this class. Um, that's also in part why we have the other classes that allow us to look at those things in other depth. But certainly, if you were to take CPRE 488, you do a lot of device interfacing and a lot of device management. That final stage that we would have there. Let's leave things right here for today. I see a lot of questions in the chat, so I certainly won't end the meeting until I can take a look at those, and maybe I'll respond on Discord afterwards. Good luck in your labs today. Uh, Show up, introduce yourself to the TA and to your classmates if you can, and it shouldn't take you terribly long for this week, but do let me know where you get stuck, and otherwise, I'll see you for quote-unquote Friday fun on Friday. Thanks.